Good morning, everybody. Welcome back to the last day of Faculty Development Program, ATAL AICT on Sustainable Additive Manufacturing in Medical Applications, UN SDG Perspectives. I'm glad to see you all ready to dive deeper into the topics and the discussions. Let's get started and make the most of this valuable opportunity. A huge round of applause, first of all, for today's guest and speaker, Professor Ravi Kumar, sir, who is a professor and head of the Department of Mechanical Engineering Department, National Institute of Technology, Warangal, Telangana. If we talk about the education of sirs, he has completed his BTech from JNTU Kakinada in Mechanical Engineering. He has completed his ME in Computer Integrated Manufacturing SIM from PSG College of Technology, Coimbatore. He has completed his PhD from Osmania University in Mechanical Engineering. He has also completed his postdoctoral research in 3D printing at Milkwave School of Engineering, USA. He has 23 years of experience. We welcome you, sir. We welcome you for the last day of ATAL FDP, and we are very happy that you are here as a chief guest and speaker for us today's ATAL FDP. Thank you, everybody. A huge round of applause, everyone, for our today's speaker, please. Thank you again.
So, very good morning, Warangal. So, I am the last speaker. Anyway, you may be enjoying for the last 5 days. This is the sixth day, the last day, sixth day. So, very good morning, one and all. So, my talk will be on the medical prototyping using 3D printing. So, first of all, let me congratulate the convener of the program and then the organizers of this program and everybody. So, thank you for inviting me. And this is the talk on the medical prototyping using 3D printing. So, and then I need to appreciate the organizers putting on this, SDGs, so especially 3, 9 and 12. So, which we can understand nowadays more emphasis on this kind of sustainable development goals by UN. Yeah, and this is going to be the outline of my presentation. Let us quickly introduce this technology. As it's additive manufacturing, otherwise called as 3D printing technology. So both are synonyms nowadays. So we'll quickly introduce this technology, and afterwards we have a 5 or 6 case studies, which I hope the other speaker, Dr. Aditya Mohan, might have given some thoughts. So we worked with him some cases, couple of cases with him, and I'm going to discuss those cases also. So predominantly 6 case studies, so which will cover different areas of medicine, that is cranioplasty one, another one is a dental, and another one is the distraction osteogenesis, the jaw reconstruction, and cancer case one, and one is oral maxillofacial surgery, that is TMJ oncolysis, so which we have got one US patent on this case, that is TMJ oncolysis, the 5th case. And 6th case, this is an accident case who needs indigenous implant. So the advantage of 3D printing in medicine, so we can provide the customized solutions. So as for the patient requirement, we can design the implant and we can fix it. Otherwise, from the market, we will get only the standard sized implants. But here, we can have that advantage. So, and then finally, what is the feature of this technology? So, the future of this technology, now we are using like titanium or a cobalt chrome or stainless steel 316 and some biopolymers and bioceramics. But the future could be like you can even print the organs. So, the organ printing is going to be the future of this technology. We will see the future perspective of this technology. So, this is the outline of my presentation. Yeah. Then why this 3D printing? As we know that you try to see the industrial revolutions and the subsequent changes. So the first industrial revolution, so it took 100 years to come to the next industrial revolution. Then first industrial revolution, we used to have the steam and water as the energy source and iron steel, But coming to the second industrial revolution after 100 years, so where electricity was the prime source of energy rather than water and steam in the previous industrial revolution. And coming to the third industrial revolution, so it took 50 years. So 100 years, 50 years, the third industrial revolution. But you try to understand the fourth industrial revolution, it is 25 years, but now we are in the fifth industrial revolution. We are in the transition to fourth to fifth. So how drastically the technology is getting evolved. So that we need to understand, then we need to we need to adapt these changes in the technology. So this is the quick evaluation of the industrial revolutions, and also the complexity and productivity is also enhancing from one industrial revolution to the other industrial revolution. So coming to this fourth industrial revolution, so where we can understand AI is going to play a major role, nanotechnology, biotechnology, material science, 3D printing is very much available here, and quantum computing and so on. So the complexity and productivity has been increased from one industrial revolution to the other industrial revolution, and the time that is very short. Maybe within 10 years we don't know what is going to be the next technology, right? So that much fast the technology has been evolving. So then we need to equip these technologies. Yeah, then what is 3D printing? So 3D printing or additive manufacturing, probably you might have exposed this technology for the past 5 days, but you try to understand the history of this technology. So the first commercial 3D printing technology came in 1987. So with the technology called SLA, and then first metal 3D printer. Though this technology started with the polymer, then it has been migrated to metal. The first metal 3D printing part has been come in during 1994, and 2014 the first AM metal part has been say fixed in a flight in aerospace industry. So these are the two industries where aerospace and biomedical is going, of course automobile. These are the three industries where any country's economy will depends on, and which we can understand this additive or 3D printing technology is going in a good rate, or the especially these industrial applications like aerospace, biomedical and automobile. And of course the sustainable development goals, so where rightly pointed out the organizers, where the 3, 9, 12. So exactly the additive or the 3D printing technology will give such a kind of say environment to achieve these goals. So the other technologies where you can, so you try to understand the first level in the inner circle, where you have this kind of the goals, sustainable goals level, so economy or society or biosphere, and of course which we can see the business function level, and the last layer is talking about the digital technologies. So 3D printing is very much available here apart from the other digital technologies. So 3D printing is one which much promising area where you can achieve these goals with this 3D printing technology. Probably that is the prime say the theme of this FDP, and of course 3D printing is going to play a major role here. And as I said, like three pillars of this technology, the applications. So as you can see here, the medical and dental together 16.4%, motor vehicle, that is automobile and automotive together 18%, 18.6, and aerospace 10.2. And among these you try to understand the medical applications. The medical applications where you have orthopedic applications, people have been using this technology, and this is the technology trigger, means the initial state or the very beginning of this technology, which we can understand the medical research, bioprinting or organ printing, that is coming in a big way. And of course dental is at the most expected or most hyped state. So the dental applications and orthopedicians, quite long time this technology has been adopted by these orthopedicians, dental practitioners, and of course which we are going to see some oral maxillofacial cases also. So if you try to understand the medical application in additive, it's coming in a big way. So anyway, these classifications probably you may be aware, like say ASTM has classified these into 7 processes, and right now which we'll be talking about medical applications, the biomaterial is going to play a major role here. You try to understand the normal material, any technology, material is so important, and of course the biomedical, where we need to understand the biomaterials that we can process through 3D printing. So the materials may be which form it is. So in a conventional process, you can take, say, if you take a machining, you have a block. Your raw material could be in a circular rod, or it may be a block. But here you have a specific forms that we need to bring your feedstock material or raw material. Either it could be in a powder form or a filament form. It may be 1.75 mm or 2.85 mm diameter. We need to have a specific standards to bring these raw material forms. Maybe it could be a filament, or it could be a sheet, or it could be a liquid. So we need to bring your raw material, any one of these forms. And then general the materials, like you can process with polymers. Again, in the polymers you have a semi-crystalline polymer, or even it could be amorphous polymer, or even it could be a thermoset polymer. So you can process almost any polymer here, and metal alloy can also be possible, and ceramics, yes, you can even process say calcium phosphate, right? So you have a ceramic medical. In terms of medical, we will try to see what are the medical materials that you can 3D print it in ceramics, and of course composites. And apart from these standard engineering materials, so you can even 3D printing will have a flexibility in terms of printing different materials. So it could be an electronic, shape memory, right, smart material, functionally graded material. So these are the advantages of 3D printing. Otherwise, you cannot do it in a traditional manufacturing process. All these materials, like biological material, something like a living tissue, or it may be a living cell, or it may be a stem cell. So could also be the material here in case of medical application through 3D printing. That's the biggest advantage here. And food, nowadays you have food printers, concrete printers in civil engineering. So where you can have all these materials. So apart from standard engineering materials, you have a flexibility to introduce your own material. So that material could be a living cell, right? So that is the biggest advantage here. And these feedstock forms, as we discussed, so I am not going into the principles of it, but in general, so your raw material could be a liquid, as we discussed, or a powder, or a solid. So the liquid may be subjecting to polymerization process. Means basically you have a monomer and you have a catalyst. So here could be a light will be used as a agent here to polymerize, or making a chain reaction here. That is called polymerization process. Or you can jet these material from the nozzle, either in terms of inkjet technology or a binder jetting. You jet the binder to stick the particles together, or you can atomize the powder particles, or you can melt and solidify, or you can join, like you have a sheets, so which you will be joining it. So you can make use of any one of these AM principle. So you have all these 7 AM technologies as we discussed, right? Say this is about how the feedstock material, this is very important, how we can bring this material, raw material and energy source, and we are going to process. So how do you get process this material? Maybe different principles here will be used, right? So with this background, yeah, so as I already said, at least 3 areas: automobile, aerospace and medical. So which we need to understand. If you talk about a heart valve or any implant, so it could be a joint, or even it could be any body part that we need to print it. So, and you are customizing as for the patient requirement. So that is the biggest advantage. You can customize the patient anatomy, right? And in aerospace also similarly, lightweighting is the major source of application in aerospace. So you can make a lightweighted structures, you can print in more lightweighted parts, like inside the gas turbine engine parts in case of aerospace industry. And then similar logic will be applicable here in the medicine. So again, you are taking the inspiration of you are trying to print a bone is much porous. So you are intentionally making a porous structure here, so which is matching the patient requirement, right? So these, at least these are the two areas where this technology is going to play a major role. And biomaterials, so what is a biomaterial is all about? So biomaterial is a synthetic material, of course it's a man-made material, so which it can replace or restore a body function, maybe your skin, maybe your bone, maybe your heart, in any part of your body which you are trying to replace, or you are going to replace or restore the function, means exactly you want to restore the any organ function, maybe kidney, liver, anything for that matter, or skin, bone. You are trying to restore or replace a particular function in your body part, right? And this body, whatever this material you are trying to put inside the human body, so that is going to be continuously or intermediately in contact with your body fluid, maybe a blood, maybe a pus, or maybe any other body fluid. It will always continuous or intermediately it will be in contact with your body cells. So then we have to be very careful whenever you are working with the biomaterials. So you should not say it should be a biocompatible. What do you mean by biocompatible? It should not create any problem to you. Once you have some plate or you have some implant which it has been implanted in your body, but it should not get interacting with your body cells. So it should not create any toxic environment. It should not create any a cancer kind of symptoms to you. So then we have to be careful. So if you are working with engineering materials, so you don't have much care about this kind of thing. It's not going to harm your engine. Engine means, okay, it may spoil the functionality of the engine, but it is not the case in biomaterials. It should not harm the human body. It should not play with the human life, right? So then this should not create any toxic or a kind of say a kind of carcinogenic impact on your body. And because of these stringent requirements, not all materials are qualified for the biomedical applications, right? And then also these biomaterials should available amicably, and it should be processed more economical way. So that is also another thing. How do you make these process these biomaterials? So that is another thing which we need to understand. So once you know what is a biomaterial, so then like your polymer, you are an engineer or a doctor, probably I can understand maybe one or two or maybe some doctor community people will be there in the audience. But like here, so you have the polymers, yes, in the polymers you have a biopolymers. You try to understand these materials right from the say head to the toe. You have a different biopolymers which it can be placed inside your body. So you can see polyolefin or PET or PVC, PMMA, polymethyl methacrylate, silicones, hydrogels. All these are biopolymers which it can be implanted inside your body, right? So various parts of your body, so where these materials can be implanted, or even it could be metals. So if you talk about the metals, even it could be a 316L stainless steel, one of the composition called 316L, or you have a titanium alloy. So you have a titanium, different grades of alloys, or cobalt chrome. So you have the cobalt chrome is another material where it serves these areas, maybe a bone fixation, bone fracture, all that applications which you can see, and nickel titanium. So another material, and of course the precious material like gold, silver. So you can platinum. These are the precious materials which you can use it for dental restorations and any other applications. So these are the biometals or the alloys. And you try to understand the ceramics like alumina. So basically it's oxide form or nitrate form, your ceramics, and zirconia or calcium phosphate. So you can make use of the bone replacement, these materials, and bioactive glasses, porcelain, carbon. So all these ceramics, bioceramics and glasses. So what I am trying to say, all these are 3D printable. One which we are working on 3D printing technology, it should be printed by using your 3D printing technology, right? So then biocomposites can also be like for dental restorations. So it may be a combination of a PMMA with the glass fillers, or it may be a quartz with the silica fillers. Yes, you can make use of these composites, biocomposites also. And you try to understand whatever so far I have discussed. So these are the 7 AM processes versus these materials. So polymers, so polymers like amorphous and semi-crystalline. So especially you talk about biopolymers, as we discussed, all these poly group. So this semi-crystalline. So you have a powder bed fusion. But anyway, I am not exploring these AM technologies here. But like you have particularly the powder bed fusion technology will process this kind of biopolymers, right? And then you have polylactic acid, PLA. Probably yesterday you might have visited the industry, like where they, yeah. So then they have a PLA is one of the material, is a biodegradable material. So you can make use it for biomedical applications. And also you have a PEEK, polyether ketone called PEEK. So this could also be printed, and this could also be printed. Yeah. Yeah. So this could also be PEEK could be printed through extrusion. That's what yesterday you might have visited this, and it can be done, processed on the powder bed fusion also. And that is about the biopolymers. And you try to understand this is the metals. So metals like titanium, you have, and you have a cobalt chrome, stainless steel. So you have at least 4 technologies will support this metal printing. So either it should be a powder bed, a binder jetting, sheet lamination, direct energy deposition. You have a huge potential here, so to print the metal and metal alloys. So this is about the AM technology and the materials, and particularly biomaterials. If you are looking at this is the region where you can, and then these are the metals which you can, some of them are bio metals which you can process it. Yeah, then once you know the technology, you know the material, then how do you develop a medical application, right? So how do you develop a medical application? So as we know that AM should start with digital data. So where do you get the digital data? So digital data in medical processing. So you try to understand, we used to have X-ray images, but after the computers, now all these images as digitized. So you have a CT data, right? And you have a MRI data. So let's say where you can take a scan, CT scan or a MRI scan for the say soft tissues for MRI, and the bone tissues like a hard tissues like bone. So you can go with the CT, right? So either it could be a CT, MRI. So your journey starts. So go to radiologist, get the CT data or MRI data in a DICOM format. So that is the neutral format which you can get it from the radiologist or the doctor. So your journey starts, right? So once you get this CT data, this CT data basically a 2-dimensional cross-sectional images. So, but these 2-dimensional cross-sectional images you cannot interpret in more better way. Then in that case, it should be say stacked together. So you have a softwares like medical image processing softwares. So what it will do? So it will say reconstruct your image. So you have taken a chest image like this, chest CT. Say one say COVID patient. So here your region of interest is a lung. So how much lung a COVID patient got affected. So but during taking your scan data, so you may be captured the ribs, that is the bone part, right? So you have the rib and you have the lungs and you have the spine. So but right now you are interested with the only the lungs, so means the soft tissue, but you are not interested at this point of time the bone like a rib or a spine. So in that case, these medical image processing softwares will give you to take a region of interest is only my say lungs. So lungs will be having a particular threshold value or bone density, right? So these are very soft, the density is very less, and these are very hard like a bone. So then you have a different densities, right? So in the software you can segregate this data whichever tissue you are interested, right? So at this point of time we are interested with the lungs. Yes, you can process these images in a, and then finally you create in a CAD model or a 3D virtual model. So that 3D virtual model is needed for your AM technology, right? So that data, otherwise you have a CAD software. So you can export your data, DICOM images into a software, CAD software, and you want to do some kind of customized implant for a particular patient. You have taken some body part of a patient, and then on top of it you are designing an implant which is specific to that patient, right? So then you can take it into CAD software or vice versa, from CAD to the medical image processing software. You design it, you sit with a surgeon or a doctor, so then you can design by taking his patient data, and then you can develop develop a kind of implant or a prosthesis, whatever it is. So then you can do, or you have designed some implant and we need to test the fitment. So you have designed some, say, hip joint like this. So taking a CT data of the patient. So before operating him, a doctor wants to check whether it is fitting properly or not. So then you can do a simulation in the software like this, right? And then we can generate a 3D computer model, or it is subjecting to, say, orthopedic applications. So whether the maximum load conditions are withstanding or not, right? So you can do a FE analysis, or if it is a cardiac application or in neuro application, so we need to do a CFD analysis, right? So you take this data to a CFD software or a ANSYS software for doing either structural or a fluid flow analysis. You can do such kind of thing, or like you want to make a physical part or a model. So then you can come to 3D printing, you make a physical object. So you have a tumor, one patient is having a tumor here, so you can give this model, sit with the doctor and let him rehearsal, or let him practice the surgery on this model, but not on the real time patient, right? And then validation, you have designed some implant, so we need to validate it. So as for the design requirements, as for the patient requirement, it is there or not. So design validation could also be done by using these softwares. So these are some of the list of softwares where you can see these softwares. So which we have at NIT Warangal, we have a Mimic software, and then still somebody is looking for a kind of open source software. So yes, you have a 3D slicer, it is an open source software, so which it can almost perform all the functions. So taking a DICOM images and segregating the tissues and reconstructing it, or either you can go with the 3D slicer or ITK Snap. This is also open source software. So these are the various softwares. Then based on your budget or the availability, so you can pick any one of these software and start taking a DICOM image from the doctor, and then you start reconstructing your images, and then you can take it to a CAD software or CAE software or 3D printing or simulation. You can do a lot of stuff, right? So once your data is coming from the patient, then you try to understand, okay, you have a software, but still why we need to have a physical model, right? So in engineering also, you have so many simulation softwares, so many analysis softwares, but still why we need to have a physical prototype or a physical model? Definitely the physical is a physical one where you can have a touch and feel. That is very much important for a doctor. So his confidence levels are high before he goes into operation theater. So let him rehearsal all these surgical planning. So where he need to cut, right, the bone, and everything can be planned here itself. And then even also you can educate the patient. This is what you should not be get panicked. So you can educate the patient. This is what we are going to do. Or you have several surgeons. Maybe you take this oral maxillofacial surgeon is going to be the part of this surgery, and also neurosurgeon is also part of the surgery, right? And then which we need to at least 2-3 specialized doctors can also be involved in this surgery. So then better they can, you have this kind of a physical model which it has been taken from the patient data, acquired from the patient data and reconstructed, printed, and let him give this model, let him go to the operation theater, or before going to the operation theater, let him do a rehearsal on these models, right? And also he can, it will also assist the where is the problem, right? So he can very well diagnose the reason for the disease or the malfunctioning, or even he can plan the surgery, what kind of instruments he has to carry during the operation, right? So all that he can, and he can rehearsal, he can simulate, he can optimize the surgical procedure in a single word. So he can reduce the operating time. So sometimes he may come out with a innovative surgical procedure. Why? Because each patient is unique procedures. But in medicine, that is not the case. Each patient is unique, and the reason for the disease or reason for the malfunctioning is different. They cannot standardize saying that I have done so many surgeries, I can do it. But no, each patient is unique, which we need to come out with the optimal surgical procedure. So where you have these models, definitely you can come out with the best or optimized surgical procedure, and you can customize the processes. This is very much important. That is, each patient is unique. So I am different with my height, and you are different, and within the same, if you put up age, your bone get deteriorated, right? So as for your requirement, so you can customize, or rather you can personalize your prostheses or implants. So you have some implant which it has been designed, and placement of the implant accurately, you can place these implants inside the body. And yeah, so this is the general procedure which we can understand. You start with taking a CT data, and then you have a software. Just now I discussed, use the thresholding or region growing, some kind of tools, and then you make a 3D virtual model, and now you have a 3D printing machine, and you have a software, so which will slice it, and then generating the supports. Probably you know how it, maybe you might have exposed yesterday also practically how you can generate the slices and how it will be sent to the machine. So once in the machine, so depending upon the material that you are using it, so your machine will build maybe polymer, maybe ceramic, maybe metal. You have the corresponding physical form of that anatomy which it has been captured from the patient. Now it is readily available here. So then how best you can make use of this bio model means, maybe for planning the surgery, just now we are discussing, or rehearsal the surgery, or you are designing some implant. We'll discuss with some case studies how you can make use of these parts which it has been fabricated from the 3D printer, right? So, and coming to the implants, so you can, what is the greatness of 3D printing in implants, medical implants? So each patient is unique, just now we are talking about. So you can personalize the implant. So this much bone density, this much porous, and this much size, and this is the geometry, and this is the shape, and this is the dimension. Exactly you can replicate. So it could be a chest implant, or even it could be a spinal wedge, right? So you can very well match the patient requirement. That is the beauty here. Otherwise, in a conventional manufacturing process, you cannot do. But this is the biggest advantage here in terms of implant. That's what you see companies like Anatomics, Zimmer, Stryker. So these are medical device manufacturers. So they are adopting this technology. And also surgical planning, like you have a FDA. So here, which we need to understand, the regulator is very important here. So biomaterials, as we are discussing, it should not harm, right? And somebody should be certified, somebody should be qualified. So FDA, that is federal, this is like a FDA, Food Drug Administrator. So you have FDA, and like in India also we have ICMR. So they will give the kind of certification. Yes, you can make use of this for the bio applications, right? So probably other speaker might have discussed about all this. So you have certainly some regulations which we need to follow, and of course the people are doing in that way. Maybe your software is FDA approved or ICMR approved software where you can make use of for planning the surgery, or for designing a personalized cast for orthopedic applications. Or quite interestingly, FDA has approved 3D printed pills. You are going to consume very soon 3D printed pills, rather than now it is going to make a personalized medicine rather than a general medicine. Why? Because majority of the time you may be taking underdosed or overdosed medicines, but now you can customize whichever dose, whatever dose you want. Exactly, you can make use of this technology to personalize your medicine as for your requirement. So that is the biggest advantage, and FDA has given clearances for 3D printed pills also in the recent time. So you can see several case studies here where this technology, maybe a huge massive tumor has been removed from the patient mouth, facial region, and then which you can match the color complexion of the patient. That is another advantage where you can talk about. and these may be a dental tooth aligners or dental prostheses or bridges or crowns. These, and each patient is unique, and his size is different. Each patient root canal or the teeth size, shape, everything is different, right? So you can print as for the patient requirement. And otherwise it will take, if you are doing conventionally, so it's a costly also, like each teeth is different size, different shape, you need to fabricate it. But here just you can take a scan of the patient, and as for the patient requirement, the size, shape, you can print it. So that is the biggest advantage. And hip prosthesis, like it may be a vestibular cups for the knee replacement. So you have all these applications in the literature you can find. So even yeah, you can try to understand nowadays this teeth aligners. Earlier clips or a wires, the metal wire or metal clips people used to use, but now you have a 3D printed aligners. So now you can book appointment, right? So Tushi, there is a company, they will come with a oral scan and they will scan your teeth, right? And they will take these images and they will send it to a 3D printer guy who prints this aligner, and they will post you, then you can fix it, or your technician will come and he will fix it. Your supply chain has been minimal. You did not, patient did not move from his place to the hospital. In fact, so such kind of supply chain is also reduced here once you have this kind of technology. And more oftenly you can notice whether he or she won a kind of a teeth aligner, right? So this is a very big business. Country like India, so we have say millions of people who needs this kind of solution, right? And each one is a unique, like say first setting they will scan and they will print it, fix it, second sitting again. So slowly it will get set, right? So at least 5-6 sittings, maybe 5-6 months. So everything will be, they will come to you. You need not go to the say dentist, right? So this kind of supply chain reduction and this kind of technology is playing a major role. Yeah, and then even you can say again, so some prosthesis. So the hand prosthesis, that is as for the patient. So you have a survived hand and you have an amputee. So this survived hand you can scan, you can use a 3D scanning technology, exactly how it looks like. You can maintain that kind of symmetricity on the other side. You can print it and you can fix it, right? And also lightweighted regs for the say this kind of child. The traditional regs are very heavy and not as for the patient requirement, but here you can customize these rigs and you can make more lightweighted rigs. Yeah, which even this is another prosthesis area where he himself has scanned and he himself has, so you have such kind of flexibility here where you can do. And this is a bespoke innovation, like again the same 3D scanning technology, 3D printing technology. So you can see a different people in the society, maybe a pop singer, maybe a professional IT professional, pop singer and football player. So you and a bike rider. But in India, Jaipur is very good in making this kind of. But we never see the the technological integration of this, but always use some white color flap or a kind of a thing, or a skin color. But now you can even match these kind of a prosthesis as for the kind of profession that he is doing, right? So then you have such kind of innovations with this. And let me come to my 6 case studies. So at least I am going to focus 6 case studies, 3 different areas. One is a dental implantation, another one is a cranioplasty. So you have the skull bone which is protecting the brain, is called cranial bone. The cranioplasty. And maxillofacial means the upper jaw, lower jaw. Upper jaw is called as maxilla and lower jaw is called as a mandible, right? So this upper jaw, lower jaw, the maxilla part, maxillofacial surgeries, at least 3-4 cases I am going to discuss about the maxillofacial, 1 cranio and 1 dental. So 6 case studies. And apart from this, like orthopedicians and other applications where you can see these applications. And first one is a cranioplasty. So cranial, if you see this patient met with an accident. So the challenge here is the thickness of the skull bone is not uniform. So we need to design an implant which is exactly fitting to the patient requirement, right? So this is from the Mimic software. You can import, we taken CT data of the patient, imported into this software, and then we have designed a patient specific implant. So, and then the fitment is very important here, and you have a cerebrospinal fluid. So that fluid will say generate in the brain and it will go all the way to the spine. So then we need to ensure this fitment of the implant is intact. So for that reason, which we used a software to design this implant, and further this will be fitted. So this implant will be fixed onto the skull part during the surgery. The fixation points, so how many fixation points? Actually here you don't have generalized standards here. Why? Because each patient is unique, as we discussed. The reasons for malfunctioning or fracture, maybe all these are different. You cannot match one patient to other patient. So then we need to give a customized solution to the patient specific requirement. So in that case, like, which could be the location, the optimal location where that cerebrospinal fluid should give a uniform pressure. So the fluid will give a pressure onto this the brain part. So then that we have done a simulation where exactly we can precisely locate these fixation points while fixing this plate onto the patient's skull during the surgery. So that simulation has been done, and for the printing, as we already discussed, titanium 6.4, cobalt chrome, and we have a 316L. That's a metal, and in the polymer we have a PEEK, PMMA. These are the two biocompatible materials which you can place. Or PEEK is somewhat lightweight, it is a polymer, but titanium is also well adopted by these surgeons. So then we have evaluated these materials which is available in the polymer as well as the metal. Yeah, and then finally we need to conventional manufacturing method. You cannot make, this is a kind of a sandwich structure, right? So you have this inner thickness is around 0.8, 0.9 mm, and outer thickness is 0.5, 0.6, and in between you have a porous structure like this. But you are not assembling like this. In the traditional manufacturing, we need to make separately, assemble it. But that is not the story here. Which we need to make this, which is exactly to the patient requirement. So how exactly the skull structure of the patient, and you are trying to match the same structure in the software that you have designed, and finally you printing it and you are fixing it here, right? So that way it will help. And the next case study is a dental implant. So the dental implant, if you take conventional practice of these dentists, so he needs implants here, means they will fix the screws, and top of it the abutment, and they are screwing this artificial teeth. So here what they do conventionally, they will take impression from the mouth with some plaster of Paris kind of material. So the taking impression from the mouth, you never get a nerve information. Nerve is inside the bone, right? So this nerve information, if he doesn't know, so always there will be a chance he may over drill or he may under drill, so he may damage this nerve. So, but conventionally what they do, that's only the one practice. They will take an impression and then they do it. But here you have a CT data, you take the CT data from the patient, right? The CT data, taking a CT data from the patient, and then you process it in a MEMS software, convert as STL file and print it and give this model to the surgeon, and they will rehearsal the surgery. So then what is the depth and what is the diameter of the drill, right? And what kind of orientation. So all that they can very well rehearsal this surgery on this patient model rather than patient during the surgery, right? And once you finalized everything. So based on this model you have drilled and then you have made as per the patient requirement. So you have a standard implants in the market, but exactly which you are giving a patient specific solution here, the implant which is specific to the patient. That is another advantage here. So next one is a mandibular distraction osteogenesis. So you can see this girl, 80-year girl. So she had this is the case the Aditya Mohan and we have done. So by birth she had this kind of problem, right? So we can see a lot of eccentricity here. So the idea here is what they do. They will use this is the another view. So where again taking a CT data of the patient and then we can reconstruct in the software, right? And then there is a device called distractor. What that distractor will do? So bone will have its natural growth. You cut the bone and then you are guiding the bone growth through this device called a distractor. So this distractor, so the patient can rotate. So one revolution, maybe 0.5 mm advancement. So it will be varying from patient to patient. So that kind of calculation we can do it on this model, right? So which we can see, this is the ramus height. So this ramus height is a normal ramus height, but this is very shorter. So means we need to stretch this ramus height until unless it reaches to this height. And also twisting, which you can see it's a asymmetry, we need to twist it. So all that calculations so will be done on this model, right? So once you do that, how much angle that it should be twisted, how much bone it should be getting stretched forward, and then you can use that distractor. With the help of that distractor, so which we can understand. Now this has been overcorrected. So the bone growth is there up to teenage. She is 8-9-year-old. Now we have done this is 5-6-year-old ago. Now this is overcorrected. So it should be final correction should be done. So in this way, where you can design that distractor as per the patient requirement. And next case study is a cancer patient, which you can see the bone anyway, cancer bone, which we need to remove it. And then removing the bone and attaining the same dimension of the patient. So means luckily you have the other side, right? So in the software, you import this data and you design this implant. So by taking the advantage of mirroring option from the survived to the defect one, so you design this is the software design, and then you print it in a 3D printer, and then you give these models to the surgeon, so they can cut and they can practice all these, where they need to cut, how much they need to cut, right? So all that thing, and then we are going to fix this thing here, right? So then again light weighting is the important thing here. So then lattice structure means one of the unique things which we need to. So this lattice structure, so means which is mimicking the porous bone nature of the patient, right? So this porous structure, a lattice based design, so instead of the solid making a light weighting, and not only that, it will increase the bone growth, the tissue formation, osteo integration. So because of that, we designed this lattice structure which is specific to the patient. Yeah, and actually this was our first attempt actually, but what they have done is they have done making use of these models and fixing these plates. They will be having these steel standard plates, and which they will be say bending and fixing on this patient models. And then finally what they have done, they will take this fibula bone, right? So God has given one spare bone which will be joining from the knee to the ankle. You have two bones. One is the tibia, that is a load carrying bone, and you have a fibula. So normally if you require this kind of situation, they will use that fibula bone. So that's what they do. But this kind of fixing that, or the shape, the size, form, they cannot carve it exactly, but that kind of a thing where this implant technology is gaining a lot of attention, right? So this is the post-operative surgery. And the next one, this is a TMJ ankylosis. So if you ask any oral maxillofacial surgeon, TMJ reconstruction is going to be the most complex surgery. Why? Because TMJ, it is a joining the joint which will join your lower jaw, upper jaw. For articulation, this joint is responsible. So you can see this patient, right? So this is what I am talking about. This joint. So by birth, she had got a fusion of one joint, one side, but God has given one clue. The other side is open, right? So one got fused, another one is released. So they, again taking a mirroring option, taking the survived one, and as I said, like this is a distraction osteogenesis procedure, the distractor. So this is the initial condition where you can see 1 mm, 2 mm like this. 21 mm, if you stretch forward this bone, lower jaw, and this is the initial condition where you can see this kind of gap, at least 21 mm gap. But now because of this distraction and this is the transformation, so they will fix this distractor device, and during the transformation, right, so maybe with 3-4 months after that, and this is the condition. So means during this, yeah, which we can see, this is what I am talking about. Say 1 mm, 2 mm like this, it will stretch forward. And once 21 mm got stretched forward by making use of that, this is the initial condition, before condition, and this is the final condition. But the major part is, this is what I am talking about. You will be having a lot of nerve system here. So if by chance, if he is not relieving this at the exact position, you have a several nerves here, and then he may cut that nerve, right? So then in the software, this is what I am talking about. By birth, she had this fusion of this joint, and in the software you can rehearsal this, where we need to cut, how much we need to cut, and taking the advantage of other side of the joint. Yeah, and then this is the design, taking the same dimensions from the survived portion to the defect one. So this is the design, and this is the prototype, and that is from the lower jaw. And upper jaw also we have a fossa component and zygometric arch. So where it will, condyle will go and sit. Yeah, this is what I am talking about. So you have this condyle, fossa, and zygometric arch, fossa, and the condyle, and all three will come, sit, assemble. This is the joint, right? This is based on this patient requirement, and this is a metal implant, titanium 6-4 we printed at our facility. So this is a titanium 6-4 material, and for the ease of them, this is the guide. Normally, what is a guide? So guide are a template, just like that. They cannot drill a hole. They must have some support, right? So for that reason, this is the guide which designed for this patient, and this is the US patent 22. It got granted, and myself, my PhD scholar and a foreign collaborator, Ian Gibson. Probably you might have read his book, Additive Manufacturing by Ian Gibson. And of course, Aditya is there inside, the doctor who is operating, and we were there inside the operation theater. And this surgery, so we have designed, manufactured, and during the surgery, now we can see, yeah, this got released. So for the past 20 years, he has been surviving. Once that fusion of the joint has been released, now she could attain normal opening. Normal opening is 5 to 6 centimeters of the mouth. And the designed implant from the upper side, that is zygometric arch and the fossa, and these are the screws, and by making use of that guide, so they drill the holes and they fix these screws during the surgery. This is from the top, and this is from the bottom, as I showed in the previous slide. So these screws has been fitted during the surgery. Now she is doing good. Actually, this video. Which you can see, now she could able to open her mouth, she is able to attain the normal opening, normal biting, normal chewing force. She has attained. Now she got engaged. Previously, the societal life of the people, this technology will also help to the betterment of the people. The societal life will be much better. Right? And the last case study I am going to discuss. So this is a basal osseointegrated implant. So this is an accident case. He met with an accident, and you can see this portion of the jaw along with the 5 teeth, the upper jaw, the 5 teeth he lost, and along with the teeth he lost the bone also, bone support also. So if you have a bone support, and these are the standard implants available in the commercial market, so you can fix it. But unfortunately, he doesn't have a support of the bone. So then no other way to help him out, we need to design an indigenous implant. But in the market you will get only these size shape implants, right? This won't work for him. Then for that reason we need to design an indigenous implant for him, so which it will exactly, and we try to understand this is not, it's not a symmetric design. Why? Because it's an accident, he broke, but you as an engineer, this is a symmetric, the fracture happens in symmetric manner, so your design will be easy. With the less effort you can do the symmetry, maintaining the symmetry. But unfortunately this is a asymmetric fracture or accident, because, and this which we can understand, this is as for the patient requirement, we have designed this implant, and then the what is the maximum chewing force, biting force, the FEA analysis has been done on this, and of course the placement of this, and this is a prototype, just we need to check it, like, so whether it is fitting or not, like they use these tools to fit it and check it. And this is the implant, titanium 64, again additively manufactured metal part, and it's a bio certified material. And then this is the support. Anyway, after sterilization, after this the other medical standards which we need to prepare this, and finally this has been during the operation, which it has been fixed here, right? And this is during the fixation, and once it got fixed, and this is what the implant will be there, permanent implant. On top of it you have these 4 teeth. It is 4 teeth, seamlessly it has been fixed here, and this is a post operative surgery. So where we can see this kind of, and this we have published in a rapid prototyping journal, the case study. Yeah, like this we may have several cases, right? Like maybe some abnormal growth of the tumor, or a cleft, or maybe the head injury. This technology will help you to give a kind of patient specific solution, right? So otherwise you cannot, buying a market, these implants, those are standard sized implants, it may not work out for the patient specific requirement. So this is the kind of a thing. But okay, so far we are discussing, like we have replaced the bone or a joint or the major bony parts, right? But then what is the future? Future could be an organ printing, means can a heart can be repaired, or can a heart can be replaced, or can a lungs can be replaced, can a kidney can be replaced, right? So that kind of thing. So then what could be the material? So any such kind of thing. So what is the material that you are going to? But additive or 3D printing will give you a lot of material compatibility. What is that compatibility? So then even you can take a cell, you can take a own cell of the patient. It may be a living cell of the patient, which we can take it, or it may be a heart. You can take a piece of heart, or you can take the living cells from the own patient, right? So that's what you can make, prepare a ink. So you can prepare by adding this cells which has been taken from the own body, and you can add some nutritions, proteins, and put it in an incubator. You cultivate it, right? So in that way you can grow some extent your organ. So and then you test it, right? What I am trying to say, This is what I am trying to say. So, and they multiply these cells, means by cell cultivation and adding proteins, nutrition to this, and multiply it the thousands, millions of cells, and putting it and testing it in a reactor. You have a bioreactor and testing it for the mechanical and other functional. Um, if it is a bone, but you don't have much challenge, it will take the loads, but not much functionality involved in case of joints or bones. But being a liver or being a heart or being a lungs or being a kidney, these are the vital organs, but it has to perform several other functionality, right? So if you take the lungs, it should act as like oxygen, like carbon dioxide. So the such kind of inhale, exhale, all that functions should be retained, right? So the challenge here is, can that functionality has been retained? So that is the $1,000,000 question. But like what the literature saying, or what are the breakthroughs in this direction? You can classify these organs maybe four categories. The first level of organs may be a simple organ, something like a skin. Yes, people have been replaced or transplanted. The skin printing has been done. People are succeeded in replacing the skin. That's a skin tissue. That's not a big deal, right? And then second level may be a bladder, or maybe third level is a bladder, but second level may be blood vessel. So you know the blood vessel, which is having a thickness, you have the blood vessels inside, right? So the blood vessels people are done. That is the second level of complexity. And bladder, yes, people have already succeeded in replacing the bladder. That may be the third level of complexity. But fourth level of complexity, if you take a liver, it may be 1 kg or 1.25 kg, the weight of your liver, and it should you have to know, it may be a transplantation, it may be repair. So such a solid mass over there, and attaining the functionality of that organ, that is a quite challenging. But maybe we never think that we are going to use a skin, a 3D printed skin, or a 3D printed blood vessels, or maybe bladder. But maybe very soon, maybe time may be the factor. It may the technological growth or the advancements may lead to able to print these kind of uh, organs maybe in future. So let me summarize my talk. So we started, I hope I might have given some overview. So how do you develop a medical case study with 3D printing technology, right? So starting with taking a DICOM image from the patient own body data, go to radiologist, get this data, and then you are the engineer, you have a software, you import this DICOM images, reconstruct it, and sit with the surgeon, and you design the implant or a prosthetic or maybe guide, or maybe any supportive device. You design it and then print it, and again you deliver it to the patient. It's a collaborative kind of research, right? Say that's what we are here like. So we have to appreciate the organizers to bring the engineers and the doctors together. We cannot do isolately, they cannot do isolately. Then we have to have a good collaborative effort, the two communities or two different domains, right? So then we have discussed like how we can take these images, how do you get processed, and how you can generate a virtual model or further a physical model for planning, or designing an implant, or designing a processes and fixing it, or even it could be some medical devices, like it could be an implantable, always need not goes inside the body. So it may be a kind of non-implantable also, like tools, guides, templates, it can be, or some supportive device like arm braces, knee braces, majority of your orthopedic applications where you can make use of technology. And finally the tissue engineering, organ printing or bioprinting. So where the material could be altogether, it's not a synthetic material normally you do, but you can prepare your own material, which it could be, say, fixing it inside your body, right? So that's what we have discussed, the future scope, maybe tissue engineering, organ printing and bioprinting. Yeah, of course, as I already said, this is not an independent work which an engineer can do or a doctor can do, right? So, definitely a close collaboration between these two domains is very much needed. And fortunately, we have a very good collaboration. Aditya Mohan, during that time, he was at Panniya, probably he might have changed to some other place. And Shekhar Reddy and Aditya Mohan, we have a oral maxillofacial kind of collaboration with them. And for dental cases, we have Dr. P. Mahesh from Narayana Dental College and couple of DST and SCRB projects. And last but not the least, my students, my BTech students, MTech students and PhD students, like you might have seen the citations of all of my students. So that is a part of their, each case study is a part of their research work, right? So I would like to acknowledge all these people here. Yeah, and these are the facilities at NIT Warangal. So we have a metal 3D printer which can print almost any metal, which we tried so far: steel, cobalt chrome, titanium, aluminum, nickel based supralloy like Inconel. So you can print the metals on this DMP Flex metal 3D printer, and we can print the polymers maybe with 16 micron layer thickness with a material jetting technology from 3D systems again. That is MJP multi-jet fusion technique, and couple of status-seismic machines, that is FDM series of machines like Dimension and the Mojo, and of course we have a small Ultimaker kind of FDM based, and we have a couple of scanners for 3D scanning, and most importantly the softwares, which we have a mimic software for medical image processing and implant designing. We have a Trimatic, this is another software, and Magix and 3D Sprint, 3D Expert, this simulation softwares for simulating the metal say environment. So these are the softwares for 3D printing softwares. Yeah, that's all from my side. If you have any questions.